So welcome to the first Faust conference, and welcome to Mainz. So we're starting with Stéphane Letz. He will present an overview of the Faust developer ecosystem. So here's your headset. Okay.
So, hello, I'm Stéphane, working at Gram in Lyon. 2 months ago I had a bike accident and I was not sure to be able to be there today. It was so I was very focused to be able to be there, and yesterday I took the train. I was supposed to change one time, and the train was cancelled, so I have to change 5 times. It's what kind of a bit ugly, but now I'm here to do this first presentation. So what I'm going to focus today is on part of what we call the Faust ecosystem. You already know that Faust is obviously the language and the compiler, but over the years we have developed a lot of tools to help people deploy the code, to help people deploy standard application plugins, deploy on different kind of hardware, laptop, mobile device, embedded devices, even deploying the web. But today I'm going to focus on 2 different subjects. One is performance testing tools. So we have developed 7 stuff and classes, C++ classes and scripts, so that that can be used to help measure the performance of the DSP code you are doing in Faust, and help find out the best compilation parameters you may want to use to have the fastest possible code. And I want also to focus on the dynamic compilation chain that we have developed over the years that allows to embed the compiler, and we have now a bunch of use cases that are interested to look at. And on top of this, and basically on top of the dynamic compilation thing, I want to explain some ideas that we have that are still not developed, but that we may develop at some time. So as a developer, if you want to try to measure the performance of your code, basically the compiler produces a C++ class with a compute method, which is the method where the actual computation is going to take place. And what you want to measure, estimate, benchmark is the duration of the compute method. So we have developed a kind of decorator kind of class that wrap a given DSP, and that you can use into your C++ code to measure the actual duration of the computation method, the compute method. This is something which is part of architecture files that, as a developer, you may want to use into your code. When we want to measure the performance of the code, what we actually want to test is how the compiler, you know that the Faust compiler can produce C++ classes with different shape. You can have what we call a scalar code. You can compile it with a vector kind of parameter, so that the code is generated in different loops. It can be, in this case, it can be auto-vectorized by the underlying compiler. And then, depending of the shape of the generated code, the computation can take more time or less time. And this is the thing we want to test. So basically, we want to explore in a kind of automatic way a subset of the possible compilation parameters you give to the compiler. So it's a quite a pragmatic approach that we use, basically. Since we have a dynamic compilation chain, based on LLVM and libfaust. So libfaust is a library version of the compiler, and LLVM is a backend that allows to generate dynamically executable code. We have developed a DSP optimizer class that automatically generates a set of different versions of the code and estimates the duration of each of them. So as a developer, you may use this kind of class to test your code. And starting from this class, we have a tool called Faust Bench LLVM, which basically is a compiled tool that uses the DSP optimizer class so that you can use it on a given DSP source code and just let it run and have the result as the best set of compilation parameters. We also do the same thing by generating a set of different versions of the C++ classes using a tool which is called Faust Bench, and the same ID, but in this case not doing the dynamic compilation way, but doing just 7 static compilation. The dynamic compilation chain, we started developing LLVM backend like in 2010, something like that. This was the first way to have the compilation chain completely in memory, so that the idea is that you can start from the DSP source and compile it to executable code without having to use an external compiler. So you can do that in memory. Obviously, it allows to develop all kind of application with a faster edit compile test loop. And over the years, there are a lot of tools that have used this technology. So at Gram, we have developed Faust Live, which is a Qt-based application using the libfaust LLVM stuff. We also have developed FaustGen, which is a Max MXP external that you can use to code Faust into Max MSP. There is a pure environment of Albert. PMix iPlug2 of Oliver Larkin. The CSUN guys, they also have developed a bridge to be able to dynamically compile FaustCon into CSUN, an application called Radium, Fauk, which is an hybridation of Faust with Czech language, done by Romain and Guy Wang. People at IRCAM doing Etescofo environment, and recently Pierre Guillot has developed a Faust pure data external that also use libfaust LLVM stuff. At Gram, we have developed another way to do dynamic compilation. At some point, we were interested to deploy on iOS, and on iOS, you cannot use the LLVM chain for some rare reason that Apple don't let you use LLVM on iOS. So we developed an interpreter backend, which is basically running a virtual machine, running a simple bytecode that is produced by the internal representation of the compiler. So it exposes factory instance model the same way we do it with LLVM backend. And this way you can compile DSP code to bytecode and run it in the VM. Obviously, it's much slower compared to LLVM path, but in some case it's even usable on regular iOS devices if you are not doing too heavy DSP. And this way you can imagine to have dynamic compilation running on this kind of devices. And we also use it, this interpreter backend, it's a way to instrument the actual running of the DSP code. And it's quite useful to find out some characteristic of the code when it's running into the interpreter backend. You can test this LLVM interpreter backend using the dynamic jack tool. So doing a very small you can, for instance, start a Faust program like the clarinet, run it, into the LLVM backend, or choose to use the interpreter backend. As you see, it takes a bit more CPU because it uses this virtual machine, which is much slower, obviously. You can design to generate the interpreter bytecode from a Faust program. So here I'm compiling the DSP source to the intermediate Faust bytecode. I can open it just to show you what shape this code has. It is a kind of textual representation of this interpreter code, and you can run it also into the directly loading the interpreter running in the virtual machine. It means you can imagine to send this compiled code on a network, for example, and have the virtual machine run it directly. We also have developed a lot of stuff related to WebAssembly. As you probably know, WebAssembly is a new low-level code, assembly-like code for the web. It was developed in 1 year ago, basically, and now it's running on all major browsers. So in Faust, we have two things. First, we have developed VISM backend directly into the language. It means we can generate WebAssembly module from the Faust language. And since the Faust compiler itself is is written in C++, you can use a generic compilator that goes from C++ to WebAssembly, which is developed by Mozilla at the beginning. It's called mscripten. So it means if you compile the compiler, the C++ compiler, with its WebAssembly backend, you can have the complete compilation chain running into the browser. So which is quite interesting. Here I have an example of this technology into the Faust editor. If you go on the Faust site to have the Faust editor, you can have a Faust code here, and if you run it, everything is running into the client side, the compiler. You compile it and you can run it. You can even activate the dynamic polyphonic version of the same code and connect it with a MIDI device, so it's here a virtual keyboard. So it means it's quite easy now for us to deploy editor kind of application running directly into the web. We also have the Faust Playground application, which use exactly the same kind of technology. And that also has dynamic compilation running inside. Or you can possibly pre-compile a static page and deploy them on the web without having to embed the compiler. So this is the first case. But the interesting stuff with WebAssembly is that you may want to deploy it outside of the web. People have developed a virtual machine running purely in C++ that you can use to run WebAssembly code outside of the web. And we have developed a tool that uses this VAVM machine to test the WebAssembly bytecode completely with a runtime running outside of the web context. So for instance, if I go back into my example, I can compile from the Clarinet DSP, I generate the WebAssembly code using the WASM backend into Faust, and then I can run it with Faust VLVM program. So now the WebAssembly code is, yes, it's running into a purely written C++ runtime, so it's real code running outside of the web, and you have the same result, and you can also measure the performance and see how WebAssembly behaves compared to a purely native code and compared to LLVM code and this kind of thing. And there are also some interesting development done into the Rust language, which will allow at some point to deploy this kind of WebAssembly code outside of the web with the CranLift WASM time machine. More experimental ideas we have that are built on top of these tools. We have developed a library which is not very well publicized, but which it was done internally like 3 years ago. The development was a bit stopped, but well, it's a kind of library that allows to expose a proxy of the Lisp Faust API so that you can deploy it on a network, and if you want to do a remote compilation and remote processing, you may want to deploy the Faust code on another machine and run it on another machine and use a NetJack audio system to transmit audio back and forth between the client and remote machine, the server and remote machine. But this idea could be used to deploy in an automatic way, to deploy DSP code and having even the audio be produced on the remote machine. This is a kind of application we want to explore at some point. It could be interesting for installation and this kind of use cases. Another idea we have that is still not done would be to deploy a cross-compilation server. So basically you would have a service running on a machine when you send a DSP source and a description of your machine, and you have the server compile it using the LLVM-based compilation chain and return you the machine code that you can instantiate and run of the client machine. And this could be interesting for machines which are not so powerful like the Bella card, and where compiling using libfaust and LLVM is quite heavy, and you may want to have this compilation step done on a server machine and just get back the machine code and deploy it on the card. This is technically possible, but it's still not there, but I would like to experiment that at some point. With WebAssembly, yes, my last slide. WebAssembly, you can obviously deploy it on the web, deploy it outside of the web, and possibly use the web as a tool to produce WebAssembly module and deploy on a machine running WebAssembly-aware runtime, like the Beza card, for instance. Conclusion, so it's a Faust ecosystem. We are still developing it at Gram, but obviously we are interested in external contributions, so you are welcome to contribute or experiment with all these tools. Thank you.
So, are there any questions? Yeah.
Thank you, Stéphane, for this nice overview and introduction. I was wondering if you also have a conclusion of for the benchmarks themselves, like which optimizations, vectorization, or code work the best, or if you actually ran or did the graphs for doing that. For that.
The thing is that it depends of the DSP. You cannot the point is that when you try to experiment, you see that depending of the DSP, you don't have the same result.
So we need to run Faust bench for every DSP and pick the best version.
Yeah,
and
exactly.
Can you automate that as well? Can
sorry?
you automate that as well? Like automatically run Faust bench and pick the best version every time?
Yeah, this tool, this Faust bench or Faust bench LLVM tool, run the same set of compilation parameters for same DSP, and at the end you have the best. It gives you the best set of compilation parameters for the given DSP you are testing.
Wow.
Yeah.
Okay, thank you.
And you can also do that programmatically using the DSP optimizer class if you want to do that into your C++ class, using this LLVM based dynamic compilation stuff. This is already used. But, well, you have to do it each time because it changed. What you see is that for a given DSP, usually when you compile, for example, in vector mode and you change the vector size, which is an internal parameter, you see this kind of curve when you have optimal size of the internal vector, and so you can see when you look at what the program tests, and well, but each time you have to change. Well, it's depends of the DSP. We are not able to have a general rule for now. So this is the point of this kind of tool.
Any other questions? So then I will invite the next one. Thank you, Stéphane.